Good evening, everyone. Hello, my name is Ian Hanna. I'm one of the solar physicists at Glasgow, and I welcome everyone to the third John Brown Memorial Lecture, hosted this year in Glasgow. Previously it was in London, 2 and a bit years ago it was in Glasgow as well. And we're here, of course, for the John Brown Memorial Lecture. John was a fantastic, distinguished scientist, which some of us in the room worked with a very long career. And for that, he was awarded not only with many prizes, but from the Royal Astronomical Society, he got the Gold Award, which is one of the most prestigious prizes that the Society gives to its scientists. So it's an incredible honour for that work. But many of us in the room knew John, and it wasn't just about the science, it was about communicating that love for the science and enthusing others about it as well. And he had many different ways of doing that. We remember his magic shows very well. But in his honour, this series of lectures have been set up where we get a different view of science and interact with the arts community to see a wider engagement, to show that science is not just for us academics or those into the astronomy, it is for everyone. And this evening we have, for a performance, so we have David Mahon, who is a nuclear physicist within the School of Physics and Astronomy, and we also have Lomond Campbell, who is a BAFTA award-winning artist and also musician, who will be talking to us this evening about songs from the cosmos, sound and vision using muons. So I will hand over to them.
Thank you again for coming out tonight to this third annual John Brown Memorial Lecture. I speak for both myself and Lomond when I say it's a great honour to be invited by the Royal Astronomical Society and to commemorate John, someone that was held in very high regard by physicists and astronomers alike, and no more so than at this university. So Ian's alluded to it, but I'm going to start off tonight's proceedings with a confession, and that is that neither Lomond nor I are astronomers. Okay, but that's not going to stop us taking you on an astronomical audiovisual journey this evening. So we may not know the difference between a pulsar and a quasar. I can just about tell you the difference between a black hole and a white dwarf, but what I can tell you is that what you're about to see tonight and hear tonight very much takes its scientific inspiration and its musical cue from events that are happening deep in the cosmos. And it's the cosmos that we start tonight's lecture focusing on. So, deep in outer space, there are huge, powerful phenomena at play at all times. We have colliding galaxies, we have collapsing black holes, and we have stars that are literally exploding. And it's these supernovae that I want to draw your attention to. So, if you think of our own star, the Sun, it's a huge ball of gas, full of hydrogen, helium, lots of different particles and atoms. As these supernovae explode, they propel vast quantities of particles through the vacuum of space. And thankfully, space.com has a very nice animation that can help explain this. So here is a red supergiant star which is about to go type 2 supernova. You can see things are starting to get a little bit exciting, and there we go. Huge explosion. So that shockwave that you've just seen, that propels all of the constituent particles from that star and propels them, or accelerates them first of all, to speeds approaching the speed of light. So in an instant these are propelled through space at speeds approaching speed of light, and these particles have nothing to slow them down in the vacuum of space. So these particles are accelerated further when they come into contact with the various magnetic fields that they encounter in space, and they will continue on their journey unaffected until they come into contact with some sort of celestial body, such as Earth. And when they do, a lot of very interesting physics takes place. So, those particles, those hydrogen, helium, many various different atoms that are propelled into outer space are what we call cosmic rays. So we'll call those primary cosmic rays. As they impact upon the Earth's atmosphere, 15 kilometres above your head in the so-called troposphere. This is the region of our atmosphere where it becomes dense enough to actually, for the cosmic ray to have something to impact on. So in this troposphere, we're getting oxygen, nitrogen molecules. The cosmic ray comes in with huge energies, and the impact literally rips apart those molecules, creating these secondary cosmic rays. So what we're seeing here is huge collection of unstable particles forming. These unstable particles, as they start to cascade towards sea level, are becoming more or decaying into something that is more and more stable, more and more longer lived, until it gets to sea level. Now, if you all indulge me, a little bit of audience participation. So if you can all hold your hand out, palm up. That's good. So at any one time, there are 2 particles per second passing through your hand. Right, you can all stop that now. Okay. So one of those particles is called the neutrino. So this is a particle that has barely any mass. It is travelling at near light speed. It passes through your palm, passes through the floor, passes through the entire Earth, and comes out the other side, almost unaffected. The second particle, now that is the hero of tonight's lecture, and that is the muon. So the muon is a charged particle, a lot like the electron, which, show of hands, who has heard of the electron? Yes, it's me in full lecture mode now. Good, good. So the electron, as you know, I'm a applied nuclear physicist, so there's going to be a little bit of nuclear physics this evening. The electron orbits the nucleus of all the atoms that comprise you, comprise everything around here, comprise this beautiful, beautiful machine that you can see in front of you here, which I realise I have not yet introduced. So this, what you can see here, this is the muonophone. Muonophone is something that you're going to hear a lot about later from Lomond. So, as the muon is about 207 times heavier than the electron. So we can get positive and negative muons. They are heavier, which means as muons pass through matter, they can get their elbows out a little bit, and they have more of an impact when they pass through materials. And my job as an applied nuclear physicist is to get the muon to tell us what it has seen on its journey through matter. So my day job is to use this muon to build 3-dimensional images of some of the most enigmatic structures on the planet, which I will talk about in part 2 of my contribution here tonight. So let's take a little step back and discuss cosmic rays in a bit more detail. So what you can see on the left-hand side of the screen above my head shows you what comprises cosmic rays. So as you can see, this is a logarithmic y-axis. That may mean nothing to some people, but basically those first 2 data points on the left-hand side show that cosmic rays are essentially over 99% comprised of hydrogen and helium nuclei, with a small smattering of contributions from heavier and heavier elements. And this is not surprising. If you think of our own star, again, it's a large ball of gas, large ball of hydrogen and helium. So when these stars explode, they're propelling out these particles into outer space. So, for the benefit of the rest of today's lecture, we're talking about cosmic rays are protons and helium nuclei, and then secondary cosmic rays, we have neutrinos and, of course, the muon. So now I want to show you a second animation. So this time we're going to take you across the Atlantic to the Windy City. So this is a video from the University of Chicago, and this shows you what happens when a very highly energetic proton impacts upon the Earth's atmosphere 15 kilometers above Chicago. So we're building suspense here. So the proton is about to come in from the top right hand side, and you can see what happens when it impacts the atmosphere. It's ripping apart those molecules, creating this huge particle shower. Now, I won't go into all the detail, but we have pions and we have kaons, and we've got lots of these short-lived particles But at sea level, and it's not helpful that we can now no longer see sea level, but you have a small smattering of particles that exist, and that is the neutrinos and the muons. Now, one good thing about this video, pausing in that rather unfortunate position, is that you can see this, where we are cutting off the screen here at the bottom. This is about 35,000 feet. So this is about 10 kilometres above sea level, which is where commercial aircraft fly. So you may or you may not know that cabin crew, pilots, they have their flight hours capped. And that's because they are subject to this amount of cosmic radiation as they fly at those altitudes. As are you if you take a flight. Okay. So, the muon. So, if you want, and this is not a plug for the Particle Zoo, but if you want to own your very own muon, you can for a pricely sum of about £30, or any particle in the standard model of physics. So, the muon is an extraordinary particle. It is a fundamental particle, which means that it is not itself comprised of any smaller particle. It literally falls from the sky. You're getting 1 muon per second passing through your hand. They're harmlessly passing through your bodies. They're passing through every single person on the planet's bodies all the time, passing through every structure on the surface of the planet and many underground also. What I'm going to show you for the rest of today's lecture, and then you'll see from Lomond as well, I want to show you how we can use this muon to build up this three-dimensional information about the structures that it passes through. And then obviously you're going to hear some incredible music that the muons are producing inside the muonophone. So the muon can do a lot of weird and wonderful things. It can make images, it can make sounds, but before we can do any of that, we have to be able to detect the muon. And as Lomond is standing there, I guess I've got the honours. Okay. So, as you can see, roughly detecting 1 or 2 muons per second. It's gone quiet, there we go. Okay. So, physicists have been detecting muons for over 100 years, whether they've known it or not. So I now want to take you on a little historical journey through the years of early particle detection. So we're going to jump back to 1912. So there's a very good reason why this gentleman is sat inside a hot air balloon. So this is Victor Hess. Victor Hess was an Austrian physicist and the discoverer of cosmic radiation. So the school of thought at the time, roughly at this time we are 15 to 20 years into the discovery of radiation, radioactivity, the discovery of particles like electrons and protons. The school of thought at the time, including by Theodore Wolff here, was that all natural radiation that is detected by scientists came from the radioactive minerals in the ground. So this was compounded by the fact that Theodore Wolff took one of his early electrometers, which I'll show you in the next few slides, this early particle detector. He took measurements of radiation at sea level and then atop what was then the highest man-made structure on the planet, the Eiffel Tower. And he found this dip in detected radiation the higher he got. So that led him to believe that the radiation was originating from the ground, which made sense. The higher you, or the further you get from the ground, the less radiation you detect. But this wasn't a school of thought that existed in the Hess household. No. So Victor Hess took 7 hot air balloon flights, taking 3 electrometers up to an altitude of 5 kilometers. And he detected this steep increase in radiation as he rose to higher and higher heights. So this was definitive proof that there is some form of radiation coming from cosmic origins. So at the time, Victor Hess was detecting muons. He just didn't know it yet. And this was how he was detecting it. So this is Victor Hess's electrometer. So this is a very early particle detector. If you're ever in the US, this is on loan at the Smithsonian Museum. And I do believe that Lord Kelvin's electrometer is also in the University of Glasgow's Hunterian Museum. And I feel quite ashamed that I've not ever went to see it. Okay, so let me briefly describe how this works. So this is a metal case. Inside the metal case, we have two metal strips, very fine metal strips, tethered at the top and the bottom, that are coupled to the external casing. If you look through the eyepiece, you see those two metal strips. Now what happens when ionising radiation, or in this case a charged muon, strikes that external casing, it draws charge to that detection point. And in doing so, it takes the charge out of those two metal wires. So those two metal wires are now charged, they have the same charge, they're very close together, they repel each other. They're tethered at top and bottom, so we have this bowing of the metal wires inside this eyepiece. So, 1912, over 100 years ago, particle physics detection literally consisted of someone looking through an eyepiece and putting tally marks on a piece of paper. And this historic measurement basically changed the course of radiation physics, cosmic radiation, to the point at which it leads directly to you all sitting there looking awestruck at the physics that you're getting taught. Okay. Now, let's fast forward a few decades. So we're now in Germany in 1933. Particle detection has improved. So what you can see on the screen here, this is a Wilson cloud chamber, named after the Scottish scientist Charles Wilson, who invented it. Inside that cloud, so the cloud chamber works by having this gas vapour, and the particle ionises that and leaves this characteristic trace. So we're now going to introduce you to Paul Kuntz, who this German physicist. He detected this very trace that you can see inside that cloud chamber. At the time, the community knew about the electron. The electron was old news. Everyone knew what the electron was. They knew the characteristic trace that it made inside these cloud chambers. It's this second trace that completely stumped Paul Kuntz. So, let me delve into what this trace tells you. So, this trace is bolder, so it ionised the gas vapour more. It also had a much larger radius of curvature, which the physics tells you means that this was caused by a heavier particle than the electron. And the final piece of information we can take from it is that it's bending in the opposite direction to the electron, which means that this is a positive particle and not a negative particle. So, at the time, scientists knew about the electron, they knew about the proton, but this was not a trace from a proton. So, Paul Kuntz had discovered some sort of particle that was positively charged and heavier than the electron. And that's as far as he got. And if we fast forward 3 more years to Seth Anderson and Seth Niedermeyer and Carol David Anderson from the California Institute of Technology, they essentially compiled all the information, all the evidence to claim the discovery of what it was called at the time the mesotron. So Carol David Anderson, he had just discovered the positron, which is the positive antiparticle of the electron, and they both also discovered the negative muon and the positive muon. They could tell that this new particle, this mesotron, was from the same species of particle as the electron, which we now know as the electron family, and they were able to then claim that this was a heavier class of electron, enough to then claim the discovery. Now, thankfully, the mesotron was quickly changed to the muon because the mesotronophone doesn't quite have the same ring to it as the muonophone. And just to round things off, in the same year, Victor Hess and Carol David Anderson were both jointly awarded the Nobel Prize for Physics for the joint discovery of cosmic radiation and not the muon but the positron. And poor Paul Kuntz and Seth Niedermeyer went empty-handed in Stockholm. Okay, so it's probably at this point that you're thinking, when is David going to shut up and let us get to this machine? Let Lomond get on stage to do his thing. A little bit longer. Okay. In fact, one slide longer. Okay. So, I think the next slide is the perfect segue between the science and the arts. So, another bit of audience participation. So, a show of hands, who here is a fan of the Marvel Cinematic Universe? Okay. I mean, that's not many, given that you're spending your Friday evening at an astrophysics lecture. Yeah, they're lying, definitely. Okay, so 24 years after Victor Hess discovered cosmic radiation, Caltech discovered the muon. And in some weird symmetry, 24 years after that, the muon, or the cosmic radiation, starts to make inroads into popular science. So this was when Stan Lee launched his latest superhero franchise, which is the Fantastic Four. So, the 3 or 4 people that dared to admit they were fans of the Marvel Cinematic Universe should already know the original origin story of the Fantastic Four. But for everyone else, and for those that are pretending, let me summarise and paraphrase heavily from this first edition comic. So, the story goes, we're deep in the space race. So, the US are competing to send the first man into space, and they get wind that their big rivals, and I'm exactly quoting, the commies, are about to launch. And you can see the fist banging down on the desk, essentially not on my watch. So the US crew throw caution to the wind. They've not tested their cosmic radiation shields, but they cannot be beaten to this punch. So they run past the guards, boot up the rockets, they launch into space, and they are bombarded with cosmic radiation. Near fatal, obviously fatal doses of cosmic radiation penetrate the shuttle, and the Fantastic Four, as we know them, are born. Now, I want to draw your attention to one pane in particular here, and that is the one at the top right of the screen. So, there are 3 voices coming from the shuttle as the cosmic rays deliver this, fatal dose of radiation. Now, I won't do the voices, but what they're saying is they're penetrating our ship, our shielding isn't strong enough, but I don't feel anything. Naturally, they're only rays of light, you can't feel them, but they'll affect you just the same. Now, it's not the blasé nature of delivering a physics lesson of naturally they're only rays of light when you're about to have sudden death thrust upon you. That's not what annoys me. It's the physics lesson itself. They're only rays of light. Now, if you have learned anything from the first part of this lecture, is that cosmic rays are high energy protons or helium nuclei and a small smattering of heavier atomic elements. So, Stan Lee was a fantastic artist, but he was a terrible physicist. And on that note, I'd like to pass you on to Lomond.
Do I actually have an honorary research position? Okay, so I've basically spent quite a long time trying to merge these 2 lifelong interests that I've had, which is building things and working with sound, mostly music, but sound in the broader sense. So we're just showing some videos of some of these projects that I've made. So when David got in touch saying, do you want to build one of your weird music machines using our muon detectors that can detect these huge nuclear events in space, of course I said, yes, David, yes, that's what I want to do. That's exactly what I want to do. So out of that interaction, fast forward a year or 2, was born the Muonophone, our beautiful child, together, which is just sitting here. I think when we got together and started working on this, we didn't think or didn't foresee that we were going to do a fringe show, which it became. So we did that last year in the Edinburgh Fringe, and lo and behold, it was a sellout success, and we got great reviews, and we've got 5 stars all over the place. No comedy awards, unfortunately, but it was really great. It was a great show, and at the end of each performance, we had a kind of Q&A. So I'm just going to use my slot here just to kind of preempt some of the questions that we got and talk a little bit about the machine, how it came about. So I guess the first thing to talk about is the look of it. So design-wise, I wanted it to hark back to that sort of bygone era of synthesizers. So big, unwieldy, clunky machines. Round the front, you can't see the front, but you'll see a video of it in a minute. It's got huge big dials and buttons and big clicky things that you can play around with. I wanted it to exist as a console, so as an instrument, but also as an installation. So it had to kind of look quite extravagant, but also be playable. If you look at the legs, it's got a kind of weightlessness, which I sort of managed to get by using this really thin 10mm bar and using these non-parallel geometric structures to hold it up. And I also wanted it to look like it was an earthly device, so that it was actually detecting something from elsewhere. I didn't want it to look otherworldly and too far out. So that's how we arrived at the look of the machine. On the back, I mean, we just saw it there, but we used incandescent bulbs, really just because I like the look of them, but it gave us a reason to use a relay module, which is what you're hearing clicking, which just gives it a nice kind of mechanical vibe, because it's all really being done digitally, so actually it's totally overkill, but it's nice to have that feel. Some of you might be interested in the tech, not everybody, but I'll tell you what we've got in there. Connected to the muon detector is an Arduino, which converts each strike, so each detection, it converts that to a MIDI note, which is just a digital note information, so within the range of 88 keys of the keyboard. So it's just note on every time it detects a muon, and it's random. And then it's also converting the strength of the muon to velocity, so you're getting volume. But then within that, I can map that out, so it's not strictly limited to just using that for volume. You can map it out elsewhere within the musical network. There's also a Teensy, which has all the controls connected to it, and that's just creating MIDI CC, so I can then map that to various parameters within my musical setup and just change things. From there, it's connected to a Mac Mini. And the idea was that everything would run standalone and you wouldn't need any of this stuff that I've brought. However, we run at a budget and I couldn't afford the license to run the software on the Mac Mini that I wanted. So what it's doing is it's spitting out MIDI data to this setup over here, and I'm just running it on my laptop. But theoretically, when David gets us more money, we'll be able to have it all standalone here. And then I suppose that just leaves the music to talk about. So, I guess, are there any electronic music producers in the audience? One? Half? Okay, one. So a lot of the time with electronic music, you're trying to sort of create these chance events. So muon detection lends itself really, really well to that. It's effectively like a random number generator, but it's muon determined, not random. So that, from a compositional perspective, that kind of causes problems, because how do you make that musical? How do you make random note on a keyboard musical? So the obvious way to do it, to me, was to create an ambient soundscape type thing. So every time it detects a muon, you'll maybe get like a swell up, a nice kind of luscious pad or something like that. That would have been the obvious thing to do, and some of it that you'll hear, that you're about to hear, is a bit like that. But I kind of didn't want to stop there. I wanted to create more of a duet between me and the muons. So I ended up writing over the top of it and trying to map out the muon data into different elements of the sort of musical structure. So it's kind of affecting quantizers, it's affecting filters, it's all over the place, and it's not just completely apparent. When you see it, it'll make more sense what I'm saying. The other thing that we did was we created visuals to go along with it. So we've managed to get that working at the very last minute. So you're going to have some visuals playing along as well. Same idea, it's just listening for muon detections, and then it's creating a sort of random event visually, or creating a kind of game of life type thing where it spreads out.
So I now realise that I am literally standing in your way of seeing Lomond perform the muonophone. So I will make this last part of my contribution quite quick. So you're going to hear Lomond let you hear the sounds of the muon. But what I want to do first is let you see the sights of the muon. And more specifically, I want to show you how applied nuclear physicists such as myself and this community of muographers around the world build detectors that allow us to see what the muon has seen as it passes into the detector. So, it's unavoidable, but if you can open your textbooks to page 1, please. I'm going to have to take you on a very, very short nuclear physics lesson. So, this, believe it or not, is my daughter's favourite book. I want my hat back, but this is obviously the better one. So, you don't need to know much nuclear physics, but if you can understand, or if you know that every atom on the planet has this strong, small positive core comprised of protons and neutrons, surrounded and orbited by electrons. Okay, that's essentially it. That's the prior information required. To be able to understand how we can turn a muon passing into a detector into some sort of 3D image of the object it's passed through, we need to understand that as the muon passes through different material, we can extract material-specific information from that muon. So, the muon, as it passes through matter, interacts via two main mechanisms. On the left-hand side, we can see muons can lose energy as they pass through an object. On the right-hand side, as muons pass through an object, they can also change direction. They can scatter from that object. Now, if we focus on the left-hand side, first of all, what you can see here is a not-to-scale representation of the carbon atom. So 6 protons in the nucleus, 6 orbiting electrons, and the appropriate number of neutrons also. So this muon comes in. The muon can transfer enough energy to one of those electrons to remove it from the carbon atom. In doing so, creating a carbon ion, the muon then loses energy because it has transferred that to the electron. Now, the more electrons that an atom has, the more chance that the muon loses energy in this way. And if you hit enough electrons, eventually that muon will lose all of its energy and stop. So that's an important thing to bear in mind when we start looking at different images that we form. The second way is the muon, as we know, is charged. So the muon can have a negative or a positive charge. We're looking here at a positive muon. So this muon comes into contact with the charged nucleus, first of all, of the carbon atom. So 6 positive charges, positive muon coming in. That positive charge, or the positive charges, are going to repel each other. So this fast-moving muon comes close to the carbon nucleus and is then scattered. This is through the Coulomb field. Now, if you no longer have 9 or 6 protons in that nucleus, and you have 92 in, say, uranium, then you're going to get a much larger repulsive force, which means the muon scatters to a much larger angle. So, if we can build detectors that can detect where Coulomb scattering has taken place and how much Coulomb scattering has taken place, then we can understand what the muon has scattered from. And we can use that to build these 3-dimensional images within some of the most, as I said, enigmatic structures on the planet. So the muon doesn't care if it's passing through an entire mountain range. It doesn't care if it's passing through water. It doesn't care if it's passing through something hot or insanely radioactive. The muon will pass through everything in its path as if it's the same thing, only changing how it interacts ever so slightly via these two mechanisms. So, the field that I work in is called cosmic ray meography, essentially using muons for imaging purposes. So, what you can see here is a non-exhaustive list of the different things that we can use muons to look inside. A lot of those things, it's just impossible to look inside them with any other technique. You can't X-ray a volcano, you can't ultrasound a carbon storage reservoir. So a lot of these things can only be imaged using this amazing particle, the muon. So if we look at the shoreline here, the nuclear reactors, nuclear waste, safeguards, this is something that my team at the University of Glasgow have been working on for the last 15 years. And I know what you're thinking, I do not look that old, but yeah, you'd be surprised. So, obviously, the UK has produced 60, 70 years worth of nuclear waste. It's obviously a material that we want to make sure is stored as safely as possible. But once you put it in a container and you seal it and you shield it, how do you tell what is going on in that container? So that we know everything is behaving as it should and we can continue storing it that way. The only thing really that you can use to look inside is the muon. So we can provide information that makes the storage of UK nuclear waste as safe as is achievable. If you start to move left on that diagram, you come to bridges. This is something my group is also looking at. So a lot of the transport bridges around the world are made of concrete. A lot of the transport bridges are 60 or 70 years old. Concrete was intended to last 60 or 70 years old. So a lot of these structures are starting to show their age. Now how do you make sure that these structures are safe for the amount of transport, amount of traffic that passes through them? If anyone travels across the Kingston Bridge on their commute, you'll know that the Kingston Bridge is closed almost indefinitely, and that's because if you don't know how the structural integrity of that structure is holding up, you have to be conservative. Our technology, the muon, could look completely passively through those structures and point or identify any defects that are deep-seated that other technologies cannot identify. So two applications showing this technology can inform safety in many different aspects of society. And then there are a few that are just plain fun, like looking inside pyramids. So one of the applications I'll show you is a discovery of a hidden chamber within one of the pyramids at Giza in 2017 that you may have seen on the BBC News. So let's think a technology using particles falling from space that can look for hidden chambers inside pyramids, that can predict how violent a volcanic eruption can be, that can travel underground, can look through nuclear reactors, can look through blast furnaces, can possibly, if you believe the word of a Canadian scientist, that they can look inside asteroids, then surely when this technology was first proposed, it must have been front page news. It must have been all over the news media, everywhere. But you would be surprised. So the very first mention of this technology was in the August 5th, 1954 edition of the Argus, which is a local newspaper in Canberra, Australia. And it wasn't front page news. No, it was beaten to the punch by the fact that bacon prices were at an all-time low, which is obviously great news if you are a lover of bacon. No, it wasn't even page 2, 3, 4, we have to go to page 5. And even then, right at the bottom of page 5, where we see this headline about an ex-boffin that may save us thousands. So, this is the story of Eric Paul George, who was a UK wartime scientist that developed radar systems for the World War II Allied effort. He immigrated to Sydney, took on a job at Sydney University, and wanted to use his newfound knowledge of muons for good. So what happened was he deployed a muon detector inside a tunnel that ran through the snowy mountains in Australia to measure how much ice and snow were above that tunnel, to inform how safe it was, what was the structural integrity of that tunnel, again, to make sure that it was safe for all the workers that were in that tunnel. essentially what he did was he deployed a detector inside the tunnel and counted the muons coming from different directions. If he detected lots of muons, more than expected, that would suggest the ice and the snow was not as thick because there's less material to stop the muon. If he detected less muons than expected, that points to the thickness being a lot higher. So again, using the information of less material stops less muons. Okay, so now let's fast forward many decades, and I'll end with what we do here at the University of Glasgow, but I want to show 3 of my favourite applications of this technology. So I'm going to borrow heavily from colleagues in this field across the globe. So first of all, 2017, this is the discovery that put meography on the map. So if you have heard of meography, chances are it's because you've seen this on the BBC News almost 10 years ago. So, a little bit of backstory. In the late 19th century, early 20th century, the Egyptian Antiquities Ministry effectively banned excavation. They didn't want to lose any more cultural heritage, so you couldn't go in with a pickaxe and look for hidden chambers within these pyramids. So how do you find what may or may not be in there? So in 2017, a group of Egyptian, French and Japanese scientists deployed muon detectors outside the pyramid, pointed them at the pyramid, and they detected different amounts of muons coming from different directions. Essentially what they were looking for was, in that direction, we've detected more muons coming into our detector than we expected. And why is that? That's because there's less material in that direction than we thought. Less material points to a potential hidden chamber. So what you can see in that smattering of white dots just above a known king's chamber is a large void that was detected inside one of these 3 Great Pyramids of Giza. Now, at this moment in time, we don't know what is in there, because again, we can't just go taking a pickaxe and digging through the sandstone. However, if you notice from the bottom right, there's this small, I actually think I can do this, give me 2 seconds. There we go. Oh, I've jumped the gun, there we go. So, you do this little part here. So, just to the left of an existing entrance into that pyramid, there was also evidence of a corridor that wasn't previously known. And it took about 7 years to get permission from the Egyptian Antiquities Ministry to drill a hole through the sandstone into that potential chamber to place a small endoscopic camera. And of course, you've all seen the image because I showed it 2 seconds ago. But there we go. This is what they found. Proof that muons did in fact point to the existence of this chamber that nobody had observed for the last 2,000 or more years since alien life forms built these pyramids. Now, since the pyramids were built, muons have been passing through them constantly. We're now at the stage where we have the technology that is able to tell us what those muons are seeing. So, 2 more applications before I blow my own trumpet a little bit and then pass you on to Lomond for his performance. So, I think this is one of the best industrial and commercial uses for meography, and that is in the market or the industry of mineral exploration. So imagine, and I guess we can see it a little bit in the North Atlantic, I'll try not to get too political, but maximising how much rare earth minerals that you can dig out of the ground is obviously big business. So if, for example, you're in Canada, which has large uranium supplies, uranium ore supplies, and you have a large nuclear power industry such as Canada, making sure that you can extract every last piece of uranium ore from the ground makes perfect business sense. So this company Ideon is a huge muon company. What you can see here is how you look for uranium ore without using muons. Each of those yellow dots or yellow lines is you drilling 300, 400 metres deep and extracting a core sample. You take that core sample and you physically inspect it Did you find uranium ore? No. Drill again. Did you find uranium ore? No. Keep drilling until you hit uranium ore, which you may never do. Now, it's obviously it's very costly, it's not great for the subsurface, it's not really environmentally friendly. But what if you only had to drill twice? Drill twice, and then in those holes that you've made in the ground, place cylindrical muon detectors that can look 360 around them. Look over there, identify less muons coming into your detector from that direction. That indicates in that direction there is high density material such as uranium ore. So this company is able to advise mine operators that they still have large, multi-million pound uranium deposits still in the bedrock that they can extract. So I think the strapline for IDEON is something like drill less, discover more, which I think is just a great selling point for this particular technology. Okay, so before I start blowing my own trumpet, this last one, the image you're about to see on the next slide, I think, as very strange and as geeky as it sounds, is my favourite scientific image. You all have your favourite scientific image here, it's not just me. Okay. So, obviously, this application shows just the power of the muon. The muon can pass through entire volcanoes, kilometres of rock, and still come out the other side so that we can infer what the muon's seen on its travels. So, if you've all seen 1990s disaster films like Dante's Peak or something like that, you'll know that you can use seismology and sulfur dioxide levels to say when an eruption is about to take place to a good degree of certainty. What they can't say reliably is how violent that eruption is likely to be. For that, you need to know how much magma at any one time can make its way to the surface. And for that, you need to know effectively how thick is the windpipe or the throat of that volcano. And again, you can't X-ray a volcano, you can't take an ultrasound monitor there, it's just far too big. But you can use muons. And this, I think this is an amazing image. This is from the just amazingly named Satsuma Iwo Jima volcano in Japan. And what you can see there on the right hand side is a density map showing what the density of the rock at the centre of that volcano is. So you can see the thickness of the throat, you can see how much magma is just sitting there waiting to come up in an eruption. And what this is able to then do for the local communities is inform how large an evacuation zone is required, because we now know how violent that eruption has the potential to be. Okay, and we're almost there. We're almost at the point where Lomond can get behind the machine. So, my team here at the University of Glasgow works on looking at nuclear waste inspection. So you imagine, we've got 60, 70 years of nuclear waste. We store it in containers that are shielded. It's shielded because we want to make sure the radiation inside doesn't get out. But by doing that shielding, you're stopping other technologies looking in. But the muon will pass through it again almost like it's not there. So we're able to then look inside the UK's legacy nuclear waste and new nuclear waste that is prepared to make sure that it is as safe as possible for its long-term storage. So what you can see here, this is evidence on the right hand side that I do get my hands dirty, albeit okay, I get my gloves dirty, but this is what a muon detector or a muon detector looks like. It's obviously a lot grander in scale, but nowhere near as pretty as the muonophone. So we have detectors that you place nuclear waste inside. Each detector has this plastic scintillator that emits a small light pulse when the muon passes through. We detect the light pulse, we convert it into an electrical signal that we then interpret using computers. Basically, instead of having these small fibres that detect the muon, inside there's a tile of scintillator that does the same thing. Takes the muon, converts it to light, converts that light into a signal that then is readable by a computer. I'm now going to show you what this technology can do. So we've got lots of different things that we can show, but on the next slide you're going to see quite an outdated, but it's a nice way of interpreting the data. So you're going to see a 3D animation that allows you to take a nuclear waste container, step through it in full 3D, a lot like a medical CAT scan, that allows you to see what is inside to about a millimetre or a few degree of resolution. So here we have this drum, thick concrete inside, steel casing. We're now going to step down in small slices. You can see the presence of this lead cube, small piece of uranium in the centre that's about the size of my thumb tip. Full 3D information without having to open the container, just using the muons that are naturally passing through it. And then we can look through vertically. You can see the contours of the drum. Again, you can see exactly where this material is, how big it is, without having to open it or without having to destroy it or disturb it in any way. Okay, so that's the vision part of today's lecture, and I'll now pass you on, switch over and let you hear what Lomond is able to do.
And if anyone has a question, we have a few moments, we can sort of do a short Q&A session about the performance we've just witnessed, if you're still processing it possibly, or questions about one of the slides beforehand. Do we have any questions in the room? Yeah, person at the front here.
No, just this thing quite a bit of a run for the money, doesn't it? But I was just wondering, that technology we're talking about, can we use other fundamental particles to have all the X-rays of a similar type?
Yeah, I guess the benefit of the muon is that it will pass through anything. So it's, in a lot of the industries that we are looking at, if you want to get the same information, you might need to use high energy X-rays, but then you have to close off the structure because you're irradiating it with artificial radiation. So the muon is great in that it will pass through anything. It's passing through anyway, so there's no health and safety implications. It's just a case of having detectors there to capture them.
Some more questions?
Yeah, so I'm going to ask a really geeky question because it's got two of my passions in life, music and physics. So actually, also the artistry there. So you talked about it being a game of life that you're using.
Yeah.
Is it some kind of cellular automated type of thing that's giving you all these patterns?
Yeah, it's a kind of reactive diffusion thing, so it's basically feedback loops. The software I use is called Touch Designer. So you can create these events that can spread out and evolve. But you're only really limited by the power of the machine that you're running it on. But I think I had like 14 scenes or sequences that you could kind of trigger and move between. So the console can operate the visuals as well. So you can kind of invert things and flip things and do various bits and pieces using the console.
So each performance is just totally random.
Within those fixed parameters, so like I created these visuals, so within these, let's say 14, I can't remember what it is, but let's say 14 scenes, yeah.
Any more questions? Yes, one over here.
So when the muons are translated into notes, do you force them into a certain key when you
Yeah.
play along?
Yeah, exactly. So it's quantized in mostly like sort of Western modes and scales, so it's kind of recognisable musically. But some of it was quite sound designy, so I think that some of the more ambient pieces have got like lots of kind of I guess glitchy sound designy elements to it as well. And you needn't do it that way. I mean, it could be microtonal, or it could be, you could do it however you want. It's just however you want to map it out to your musical network system.
Any other questions? No? One of the first things.
This is probably a question everybody else will know the answer to. So when neurons are travelling, can they be diverted from their path, or was there a trajectory to keep going?
They can be minimally affected, so they're travelling at near light speed. So even as they scatter from the heaviest of elements, they're still only scattering through 1 or 2 degrees. It's a very, very small scattering that our sensitive detectors can pick up. They also, they've got magnetic moments, so they can be diverted magnetic fields, but because of the sheer velocity they're travelling at, any effect is fairly minimal.
We had another question here.
Yeah, it was just on the display with the light bulbs, the direction the bulbs are lighting. Is that related at all to the direction the muon is coming down when it's coming up through the Earth from the other side?
So no, but I wanted to do that. So the idea was that it was going to be a kind of 16-step sequencer, and depending on where the muon was detected within the detector space, that would sort of determine what part of the sequence it jumped to. However, I wasn't able to do that. I ran out of time and brain power, and I couldn't manage that. So what we did was we just created a little nice bloom animation just for the sake of the audience who can't see what I'm doing here. But I mean, I guess this is phase 1. So
Phase 1, yeah.
phase 2 we'll try and get that muon determined sequencer working.
So when there was a burst, it wasn't really a burst, it was a single, each kind of flourish.
Yeah.
Like,
Yes, exactly. Yes, single trigger effectively. Yeah.
Yeah, I have a geeky question.
You're the best kind.
When you were talking about the practical application, you about direction.
Yes.
How on earth do you get directionality if these things are coming at you from all directions?
So I guess if you look at the nuclear waste applications, you've got a detector above your object and a detector below. So most muons come vertically down because that's the shortest point between where they're produced and sea level. So we effectively detect the muon as it enters an object and then as it exits. So this is a very exaggerated scatter. But what we do really is project both vectors into our unknown volume to the point at which we assume the muon has changed its trajectory, and then we can then measure that angle, and it's that angle that is material specific. So we could then know just from those two vectors, we can complete the data set and say that at that point in this unknown volume, there's a material that correlates to that particular scattering.
Okay, I think. Oh, sorry.
I'd just like to say that John would have thoroughly enjoyed tonight. Thoroughly. It's absolutely on his plane or whatever. He was passionate about astronomy, but he was passionate about music, art, philosophy, magic, of course. And all I can say is you did him proud.
Thank you very much.
Can't add any more to that other than saying the drinks are outside. If there's any other questions, you can grab me and David during the reception. Thank you.
Thank you, everyone.